Hello, everybody, and welcome back to this month's Future in Space Hangout. My name is Tony Darnell. I work at deepastronomy.com, and we are here to decide. We got a really great hangout planned for you this month. We're going to be talking about HabEx, which stands for the Habitable Exoplanet Imaging Mission, and it will be the first mission capable of directly imaging Earth-like planets around nearby stars, searching for, not just searching for habitable conditions of those planets, but possibly even signs of life. And so we're going to be talking about this with our guests today. But if you have not been to one of these hangouts before, let me give you a little idea of what we're trying to do here. The Future in Space Hangout is a monthly hangout that is endorsed by the American Astronomical Society and the American Astronautical Society that helps us bring forth, it tries to take a look at the future of our humanities endeavors in space, and we take a look at not only space travel but also the future of science as well. For example, last month we talked about the LUVOIR mission, which was a big telescope coming up down the pike, where they're going to be looking for a lot of different things, early stars and galaxies. And if you haven't seen that, I would highly recommend you go back and check it out after we're done here, of course. And then, but this month we are sort of extending that discussion, where we're going to be talking about the HabEx mission, which is something I just outlined for you here. It kind of gives us a chance for the members of these organizations to highlight their science, their technologies, and for us to kind of get a sneak peek at what's coming in the realm of humanities endeavors in space. And since we are a hangout on air, we very much want you to interact with us, and the best way to do that is going to be by using Twitter on the hashtag Future in Space. You see that? There's the hashtag right there on my lower third. So if you guys will use that, I've got it sitting right here on my laptop screen, looking at it scroll by, and I'm going to be taking a look at this throughout the hangout, where we can hopefully get your questions and comments. I already see Andrew Planet. Hi, Andrew. It's good to see you there again. And so that is the best way to interact with us. We also, in the future, not this month, but next month, I will have my chat window available on deepastronomy.com. It's being written as we speak, and I'm looking forward to being able to use that next month. So anyway, that's how you can interact with us, so please do that now. But before we get started, let me introduce everybody. I'll start with my co-host, Dr. Harley Thronson. Hi, Harley. Welcome back.
Good afternoon. As always, good to see you every third Friday of the month.
Every third Friday of the month, where we do our Future in Spaces stuff. And Harley is an astronomer and astrophysicist, well, an astronomer, that's the same thing, at Goddard Space Flight Center. Welcome, Harley. He helps organize these. He gets our guests and he wrangles all the topics and puts them on our schedule.
Yes, I'm the guest wrangler.
You're guest wrangler. Okay. So let me introduce our guests. I will start with the way you're lined up on my screen from left to right. Dr. Bertrand Menenson. He is from the Jet Propulsion Laboratory. He's the survey scientist for HabEx, and he's here to talk to us a little bit about some of the technology. Welcome, Bertrand.
Thank you, Tony.
Also joining me is Dr. Rachel Somerville. She is the Downsborough Chair. I had to be careful, be told how to pronounce that, in astrophysics at Rutgers University. Hi, Rachel. Welcome. Also joining me
Hi.
Oh, that's why we had to mute you, because it was an echo. So thank you, Rachel. Also joining me is
mute me again.
Okay. Well, right now I don't hear the echo, so we're okay. I'll leave it for now. Dr. Scott Gowdy from The Ohio State University. He's at JPL right now on sabbatical, I guess, and he's the co-chair of the HabEx mission. Hi, Scott. He's also a good friend of Alberto, who couldn't join us today for some reason.
Hello. Thanks for inviting me. It's very sad Alberto can't be here.
Yes, but I'm sure we'll get by with that.
We'll do him proud.
We'll do him proud. That's
we'll do
right.
our best.
Okay. All right. So HabEx, it is a mission that is currently being envisioned as the next great flagship mission that comes after the James Webb Space Telescope and WFIRST. Now, you've heard us talk about these missions in past hangouts. These are things that were decided on and voted on. I don't know if it was a vote, but on this thing called the decadal survey, and that's this thing that astronomers use to decide what's most important and what are the things that they want. And so this is being why don't you give us a background on it a little bit, Scott? Is it being planned now? Is it being argued for? What's the status of HabEx?
Maybe all of the above. So, so about a year and a half ago, the head of the astrophysics division at NASA, Paul Hertz, solicited or basically charged the astronomical community to come up with a set of missions to study in detail for the next decadal survey in 2020. And out of much discussion and a little bit of contentious arguments, 4 contenders came about, and I think you've already heard about 3 of them: the Far Infrared Surveyor, the X-ray Surveyor, and LUVOIR, the Large UV Optical Infrared Surveyor. And the 4th one is our HabEx, as our cute catch name for the Habitable Exoplanet Imaging Mission. And so these are 4 possible missions that are being studied by science and technology definition teams, basically to be delivered to the decadal survey as possible contenders for the next large mission to be launched by NASA after JWST and WFIRST, as you say.
Right. Now,
So,
I just want to give you kudos, first of all, for your acronym, because anybody who follows the work that I do in the podcast that I'm doing with Carol Christian, we just did a podcast getting ready for OSIRIS-REx, which is going to launch on September 8th. And I'm going to just say right now, that is a cool sounding acronym, but I'm not going to even tell you what it stands for, because it just goes on and on.
yeah, I mean, we may or may not end up being the best mission out there, but we certainly have the coolest name. That I'm convinced of.
Well, you certainly have yeah, and it's easy to say and it's easy to understand. Habitable Exoplanet, or HabEx. I can definitely deal with that.
So our team is a team of 16 astronomers, engineers, and astrobiologists. So Bertrand and Rachel are 2 of the members. Sarah Seeger is my co-chair. And you know, the goal of our mission is exactly what you said. We aim to be the first mission to directly image Earth-like planets, so planets with thin atmospheres that orbit in the habitable zone of their parent stars, the right range of distances where they get enough energy from their star that they can have liquid water on the surface. And then we hope to take those habitable planets, if we should find them, and image them and look for signs of habitability, water, and maybe even signs of life.
Well, to me, and maybe Rachel, you could comment on this too as we talk about it a little more, but to me, one of the things that I'm particularly excited about is this ability to directly image Earth-like planets. Is that a step beyond what JWST is going to be able to give us? Rachel, can you comment on that?
That is definitely a step beyond what JWST will be able to give us, although I'm going to punt that question back over to Scott, since I am actually not an expert on exoplanet science.
Okay, Scott, well, maybe you could elaborate then. Why?
Sure. So, you know, I mean, we talk about taking an image. What does that mean? I mean, we're all familiar with taking an image with a camera in our cell phones, and if you could pull up this digitized image of the Earth, Tony, it would be great. So, you know, our cell phones have these digital cameras, which are composed of pixels. Each pixel in and of itself is a little mini camera, and so you get these digitized pictures. And we would love to have a picture of another Earth orbiting another star that looks like this, but this is well out of the range of our technology.
Well, yeah, but this looks pretty crappy as a picture of the Earth.
It looks pretty crappy, but it's basically you know, hundreds of years beyond the technology that we have now. It would require a resolution that's something like 100,000 times better than Hubble, or a telescope that's roughly 160 miles wide, or 10 times the length of Manhattan. So that's not going to happen, but if you could pull out the next image, which is a very famous image called the pale blue dot image, this is something we think we know how to do. And this is going to look a lot less impressive to people, this pale blue dot image. And what you see is a bunch of streaks. Those are actually artifacts of a camera, but there's a tiny little pale blue dot, which is unresolved. It's less than the size of a pixel. That pale blue dot, my friends, is the Earth, an image taken by the Voyager spacecraft when it was about 40 times the distance of the Earth from the Sun. So that's the entire of humanity at the time that picture was taken, contained in less than 1 pixel. That is what we think we know how to do. Now, you might think this is entirely hopeless. Like, what could we possibly learn from that pale blue dot? But it turns out you could learn a lot.
So you're telling me that by just a dot like this of less than a pixel, we could learn a lot about the planet itself.
Right, and the reason why, and if you could pull up the picture of a spectrum of the Earth, that would be great. The reason why is that spectra, in other words, taking the light from that pale blue dot and dispersing it and separating it into the other spectrum. it's a spectrum of the Earth.
Other spectrum. Okay.
The component wavelengths turns out to be very powerful, because we can ask, why does the Earth shine? That's not it either.
Well, we went through all this trouble of putting them in order, and
it should be figure 3, I think.
Okay, it's
anyway,
a spectrum.
We'll work on it. I'll keep talking meanwhile. Anyway, so why does the Earth shine? Well, it shines because it reflects sunlight, but that means that the light has to pass through the atmosphere of the Earth twice. And when that happens, the atmosphere isn't completely transparent, although it's mostly transparent. You can see the sky's blue. That's because there's scattering off of small particles in the atmosphere. But there's also molecules like water and carbon dioxide and ozone and methane. And those molecules will absorb light in specific wavelengths. And so if we can take that spectrum, then we can actually get a thumbprint of what is in the atmosphere of that pale blue dot, even though we're just looking at that unresolved image. And so we can look for things that might be signatures of habitable worlds, like water, which we think is essential for life on our planet. Carbon dioxide, which keeps our temperature warm enough to have liquid water. Methane, which comes from mostly biological activity on the Earth. We can even look for a blue sky that would indicate a thick atmosphere, and things like that. So these are all pieces of evidence that the planet might actually be habitable, and in principle might even have life on it as well.
Are you sure it's not this one?
No, that's not that one. But I'll get to that one next if you're ready for it.
Yeah, let's do it, because I got it up. I can't find it. I'm not sure what you're talking about. Sorry.
So that's the main goal of HabEx, is to try to take these spectra of these little dots and see if we can find signatures of both habitable conditions and maybe even life. But in order to do that properly, we really have to put those spectra in the context. So HabEx is going to be able to do much more. It's going to be able to survey all of the planets in our nearest neighbors, and those planets might be very, very different than the planets in our own solar system. So we know from Kepler, for example, that there's an entire population of planets called super-Earths with mass between 1 and 10 Earth masses. There are no such planets like that in our solar system, but we think that it's possible that those planets could even be habitable. And so one of the things we want to do is we want to take spectra of all the planets of our nearest neighbors and learn their personalities, and find out about the Joneses and the Johnsons and all of our neighbors in our that are all the planets that are orbiting the stars that you see when you look up in the night sky. So that's HabEx overall goal, and there's that spectrum of the Earth where you can see all the signatures of things that indicate both that the planet is a nice place where we might want to live, but also actually contains life as we might know it.
Okay, so these are the kinds of things that we're hoping to get out of HabEx in the future, and this is a lot of information. I mean, I'm sorry it took me a while to get it up here, but as Scott was saying, there's a lot of information that can be gained by where water vapor might be absorbing things from the atmosphere and whether the carbon dioxide is absorbing things. So you can see a lot of these absorption features in a spectrum that helps you understand a little bit more about the planet itself. So really cool. Okay, well, good. So this is what we're hoping to learn from this instrument coming forward. I guess the thing I'd like to so you're talking about the spectra and what they can tell us about the planets when we image them. How do you take these spectra?
So that's the trick. This turns out to be really hard. Now, astronomers like really hard problems, so we're not super daunted by this, but just to give you a sense of how hard it is, Earth-like planet at a distance of something like 30 light years, which is the typical planet stellar system we're going to be studying, is incredibly faint, but it's not actually any fainter than things that we've imaged with Hubble. The real problem is that it's sitting right next to a star that's so bright that you can go and you can see it with your naked eye. So you're looking for something that's as faint as anything we've ever imaged next to something you can see with your naked eye. So the Earth is 10 billion times fainter than the Sun. And the problem is that very faint object is sitting right next to the star, so it's hopelessly lost in the glare of the star. So a very common analogy that you'll hear when we talk about this is that it's like trying to see a firefly next to a searchlight. So you can pull up that image maybe. And and a firefly is just, completely lost in the glare of that searchlight. But the catch, right? The catch, and if you can pull up the next figure.
Oh my goodness! Okay.
That firefly, to put this to scale, that firefly and that searchlight are sitting in Los Angeles, and you're trying to see that firefly when you're standing in New York City. So that's the common analogy everyone used. I actually went and looked this up one day because I was wondering how accurate this was. It turns out that this analogy is incredibly flawed. A firefly is actually almost 1,000 times brighter than compared to a typical searchlight than the Earth is compared to the Sun. So in other words, this is actually 1,000 times harder than what I just said. This analogy of the firefly and the spotlight in LA when you're standing in New York. So it is an incredibly hard thing to do.
Here, and you're saying that's an easier problem to.
It's 1,000 times easier than what we're trying to do.
All right, cool. All right, presumably, and so what's the solution? What do you do to block this light out?
Well, I'm going to let Bertrand answer that because he's the expert on the technology.
Okay.
Right.
Okay.
So obviously it's a very difficult problem as Scott just said, but we think it's really within reach, and NASA, the science community at large, have been working on this for 1 or 2 decades now, and we have a couple of solutions that we think would be able to do the job. None of them is easy, but they are very different, which is a good thing because it gives us probably more chances that one of them is going to work. And we are really getting close to the required level of starlight suppression that Scott was mentioning. So there are really 2 techniques, as I said, and the first one is called the star shade. So that's I think there's a little if you want to. Okay. Yeah, if you can put that little video, that's gonna be better than 1,000 words to describe this.
All right, I've got it playing, so go ahead.
All right, thank you. So yeah, what you're gonna see here, of course, is an animation that shows the case where both the star shade, which is this giant shade, is being launched together with the telescope, and so once in orbit, they separate from each other. You can see the star shade deploying, and we'll get back to that. And the star shade is huge once deployed. It's tens of meters in diameter, and it's going to fly away from the telescope. And then, as the telescope points a star, this star shade needs to be placed exactly in the line of sight from the telescope to the star. And when you do that perfectly, which you're going to see here, you start to block the starlight. And of course, the planets, which are slightly
Jupiter magically appears. Look at that.
Yeah, exactly. That's right. Yeah, in a little animation like this, it seems easy. In reality, of course, it takes a lot of hard work in the lab to do this. So what you can see here is the deployment mechanism for this star shade. So the star shade, as you saw, is like a little flower, or big flower, I should say. So it has a central core, and it has these petals which need to be deployed very accurately.
Now, this is a scale model, right? This isn't the full size.
This is roughly a scale model. It's like, I think it's a 24-meter model, and for HabEx, we're probably talking about something slightly bigger, but not too much.
Okay.
The bigger the telescope, the bigger the star shade. So it really depends on the actual size of the telescope. The incredible thing is that the positioning and the shape of these petals need to be accurate within 100 microns or a few hundred microns, and the lab testing so far really demonstrate that, and they demonstrate also repeatability of this deployment with this kind of accuracy. So
now, when you say accurate, you mean the tolerances that they're built to have to be to within a micron?
Yeah, to within a few hundred microns. I mean, so basically, this is the analogy. This is similar to what you would do in order to see a bird or a plane passing in front of the sun, right? You would just block the sunlight and try to see a faint object around it. The only difference here is that the star shade has to have a very peculiar shape in order to really cancel the starlight and cast a very deep shadow that the telescope will sit in. So if the shape of these little petals is not exactly right, then you're going to get some residual starlight scattered and making it to the telescope, which is exactly what you want to avoid. I mean, the beauty of this technology is, in theory, is you've gotten rid of all the starlight before you even reach the telescope. So the telescope itself doesn't have to be exquisite, but the star shade has to be positioned and has to have exactly the right shape for this to work.
Yeah. Now, for those of you who've watched our Hangouts before, this is a bit of a review because we've done one on star shades as well. We know that if you've not seen them, then what Bertrand is saying is really important stuff. The shape of this thing, blocking out the starlight before it reaches the optical train, is something that really helps out the sensitivity of the telescope. And if you for example, what a lot of people do, and I think even JWST has got these things called micro shutters, which they're trying to use to block out the light that's already that's been collected by the optical path. That's a little bit of a different problem than what Bertrand is describing here, by putting it way out in front of the telescope and blocking it, and by having the shape that it has, which has been modeled out quite a bit. Or it has been modeled to reduce this diffraction effect, or the bending of light around sharp surfaces. Then you get the ability to see these dimmer, much dimmer objects that Scott was talking about right next to it. So I have a quick question while we're on the topic of star shades, and I don't know if I just found this out yesterday, that Webster Cache. Are you guys familiar with Webster Cache?
Yes.
Everybody is familiar.
Yes. Now, for those of you who don't know who Webb Cache is, he was, first of all, my astrophysics instructor at the University of Colorado. So he was I had him for 2 semesters, great instructor. But I guess he holds a patent on star shades. Am I right?
I didn't know that.
I think he does.
He wrote one of the first papers describing the concept.
Yeah, he was the first people to work on this.
He literally is the father of star shades.
Yeah,
who is?
He's the father of star shades.
He's the father of the. Well, okay. Well, that just makes me proud, because he was my instructor, and I just want to give a shout out to him because I just found this out yesterday. I did not know that he played an instrumental role in this design. Now, he's also got designs for doing this from balloons, from the high and the upper atmosphere as well. And so that was just a little tidbit I just wanted to share, because I just found that out yesterday. So hat tip to Webb Cache for the star shade idea. And now I just want to clarify also, these things, you showed us the unfolding of the model in the clean room there, and it's going to be a little bit bigger, you say, but these have to be precisely matched, right, Bertrand, with whatever telescope. So if you've got I don't know, let's say a 30-meter telescope in space, or however big these things are, this has to be correspondingly sized, correct? Yeah,
that's right. I mean, basically the size of the star shade scales almost linearly or a little bit faster with the telescope diameter. So, for a 5-meter telescope, say, you probably could get away with a 30 to 50-meter star shade. But if you start to talk about a giant telescope of 30 meters, then you're talking about 200-meter star shade. It starts to be really encumbrant.
Right. So, yeah, I just picked that up. But yeah, I know that there are plans, however, for really, really large space telescopes. Right. And if they were going to incorporate a star shade thing, they would need something suitably larger. And these, how far away are these? Like, let me just pull this up again. So here we have the real quick animation of this. How big would the star shade be? Or how far away, I guess I should say, from the...
Yeah, so that the distance to the star shade also depends on the size of the star shades. So it's typically tens of thousands of kilometers for a telescope of 4 or 5 meter diameter and a star shade correspondingly 40 meter in diameter. So that's why it becomes really difficult to consider star shades for much larger telescopes and much larger star shades, because you need to push them even further away. And of course, as the star shade is being pushed away, that means that it takes a lot of time to move the star shade from target to target. If we say like the star shade is 30,000 kilometers away, for instance, and you want to move from one star to another, which is maybe 10 degrees away in the sky, well, you're going to have to move your star shade by 5,000 kilometers, right? So to point this new star, and that's going to take, typically a week or something like this. So that's about
so slewing
as much
is a
as we
real
can
issue.
tolerate. Yeah, slewing is a big issue. It means that, fortunately, we're going to be staying on these faint targets for a long time as well. So, you want at least to stay as long as you slew. But if it takes, a month to slew, then you really have a very low duty cycle. So there are some practical limits to the size of the star shade that you can use, and then probably the size of a telescope that can work with the star shade as we understand it.
But this is one of the things that motivates the other sort of starlight suppression technology.
That's right. So yeah, I don't know if we can talk about this other method, which is diametrically opposed, and that's what I kind of find fascinating in this is we have two solutions, one which is microscopic, we just described, and another one which is completely different, which is basically using some very small masks or series of masks in the optical train of the telescope at the back end of the telescope. So they are on board, and they're very small. They're from the size of a mirror to the size of a pinhole, and that's what we call a coronagraph. So
that's what I guess I was alluding to earlier with some of the putting them inside the optical train, little tiny occulters, yes. Right? Little discs that block out light that are in the focal plane.
Yeah, some are in the focal plane, some are in different focal planes. So in fact, when we talk about a coronagraph, we talk about a system of masks in different planes, and the first coronagraph actually was built in the 1930s by an astronomer called Bernard Leo.
That's right.
To study the solar corona. So
that's right.
If you're interested in looking at the chromosphere or faint structures around the sun, you need to block the sunlight. So the first coronagraph, the simplest one, was built by this guy a long time ago, and it already had some of the major elements that we know a coronagraph has to have: a focal plane mask, and then what you call a Leo stop. And this has evolved tremendously over the years. I mean, it's been 80 years that people have been using coronagraph, and progress has been made over the last 10 or 20 years, which is very spectacular in that field.
Okay, but based on what I know about chronographs, Bertrand, and I just want to spend a couple more minutes on this, and we're going to move on to the next thing. But the thing that I know about chronographs is they kind of have to be matched to what it is they're blocking, right? I mean, the sun is roughly a half degree or so, right? So you would need your ground-based telescope would need an appropriately sized Leo stop to block it out. Wouldn't you need to have some kind of matching ability to block out the lights of a star, or does it not vary that much?
Yeah, to some degree you're right. I mean, stars are of course much smaller in size, in angular size, than the sun. It's, they're typically, for the stars we are interested in, they are 1 milliarcsecond in diameter. But your sensitivity to basically resolving that stellar disk gets higher and higher as the telescope gets bigger. The bigger a telescope, the more you resolve that little stellar disk. So in practice, what's going to happen is you're not going to point to the star perfectly, so you're going to have what we call some pointing jitter, and that's roughly equivalent to the size of the star for this type of star. So we need to point to better than a milliarcsecond anyway, and so it's.
So which one is HabEx going to use? Is it going to use the macroscopic or the microscopic solution?
That's the good
star
question.
Shade or the chronograph?
That's a good question.
We kind of joke saying that we like to have both belts and suspenders here, but there are actually serious reasons for doing that. So on one hand, it's probably adding robustness if you have like two different techniques which are so independent of each other that they really represent some viable independent solutions. The other reason, and we need to work more on this as part of the study, is there are possible ways that using the two in conjunction is actually better than using either one of them alone. And we'll have to work more on this. But there are solutions where you could use, for instance, the coronagraph, which is very nimble to do some blind searches of planets. And then once you've discovered planets of interest, you want to spend a lot of time on them, then you would use the star shade. You would position the star shade in front of that particular star. So there might be ways to use both together other than just
okay, so the answer to which one are you going to use is yes, right?
Well, the answer is that's why we're doing the study, Tony.
Okay. All right.
Either one or both, or the fair answer to that question is we don't know yet.
Okay, cool. Well, all right, good. So so we've got this telescope that you're planning with some method of blocking out the star's light that's highly able to resolve these exoplanets, and so that we can maybe get a sense of what their habitability is, whether or not we can see signatures and signs of life. But Rachel, let me get you involved here. I'd like to ask you, what else can we do with these telescopes?
Well, a lot. So this is one of the exciting things about HabEx, is that without compromising our ability to do the exoplanet science, we get almost for free, or at least for a very moderate increase in price, the ability to do some really exciting astrophysics to study not only stars but also galaxies. So one of the hardest unsolved problems that we have in the field of galaxy formation is trying to understand how we get from the Big Bang to the Milky Way. So somehow all of the primordial hydrogen and helium that was around shortly after the Big Bang has managed to collect into galaxies and be cooked into stars and into the heavy elements that we need in order to form planets and life. So there's a nice connection actually there between the larger scales and the smaller scales. So one of the puzzles is, if you look at the diagram, I see you have that up there, in the sort of bottom right, this is showing the mass of stars in galaxies on the y-axis, and then on the x-axis, the mass of their dark matter halo, or the total mass of all of the material that's gravitationally bound to the galaxy. And the sort of dotted line shows what we would expect if all of the gas in that gravitationally bound system could collect into stars and form stars. But what we actually observe is that star formation is very, very inefficient. Most of the gas that we expect to be in stars is in fact not in stars. And it's not in the interstellar gas that we see.
It's this dark matter halo, right?
No. So the gas that should be inside the dark matter halo is not inside the dark matter halo, if that makes sense. So for example, we think that there's around 16% of the total density is normal material, right? Atoms.
Right.
But most of that material is not in stars and galaxies. So the question is, where is it, right? So if you look in the little picture on the top left there, the very left picture shows a hydrodynamic simulation of galaxies, and that shows the stars in the galaxies. What you see to the right of it is the distribution of gas, and what we predict in these simulations is that when stars form and when supernovae explode, they kick out a lot of energy into the gas that's around them, and it's enough energy that it can actually kick the gas out of the galaxy altogether. So this explains why we don't see so many stars in these dark matter halos, because the gas has been sort of spewed out into what we call the circumgalactic medium. So this predicts that galaxies should be surrounded by these great rubbish heaps of ejected gas. Of course, we'd really like to see that gas and be able to study it and be able to study how many heavy elements are in that gas, but that gas is incredibly difficult to see. So this is one of the very exciting projects that we think we can do with HabEx. If we have ultraviolet capability, we can look at a background quasar, or anything bright really, so the quasar is just like a giant light bulb, and then we can see places where these clouds of gas have absorbed the light from the quasar. So we see little dips in the spectrum, very similar actually to the spectrum that we were looking at of the planet, but in this case we're looking at a spectrum of a quasar. So wherever light passes through the gas clouds, it gets absorbed with a particular fingerprint, just like Scott was saying. Each element has its own characteristic wavelength where it absorbs the light, and so you can actually identify, aha, there's some oxygen, there's some carbon. And all of those lines, or many of those lines, are in the ultraviolet. There have been a few studies done with Hubble where we've seen these signatures of absorbing gas, but unfortunately Hubble is rather small, right, compared to what we think HabEx will be, and its lifetime is finite. So we don't think that we'll be able to study enough systems to get a full picture of this circumgalactic gas, which we actually think contains most of the normal matter, or what astronomers call baryons, in the universe.
Okay, you brought up a couple things I want to respond to, and I don't know if it's better if Scott talk about this or Bertrand, but you said a couple of things. First of all, and again, forgive me, when I'm driving the internet and then I'm showing the images, sometimes you're talking and I may not have heard you say this, but HabEx, in addition to looking at these planets and helping you to see the gases in these galaxies, like you were just talking about, you mentioned that the UV is going to be hopefully one of the wavelength capabilities. What are I don't think we've talked yet about the wavelength ranges here for HabEx, have we? I mean, you mentioned UV, which, by the way, no one else is doing right now, and there aren't any plans for any UV telescopes going up. JWST is going to be infrared. WFIRST, that's another infrared telescope. So UV is something that right now only Hubble can do. And as Rachel just said, it's small. It's not a big enough telescope to be able to do the kinds of work. So I guess my question to you guys is, first of all, can you comment on the wavelength range of HabEx? And did we also say the diameter that we're hoping to get, the kinds of aperture sizes that we're hoping to build here? Scott, would that be one for you?
Sure, I can briefly talk about that. I mean, the 0th order answer is we don't know.
Okay.
We're still in the early phases of the study, and we're trying to decide. In terms of the habitable exoplanet application, if you remember that spectrum that you threw up, anywhere between about 300 nanometers, so that's somewhat blueward of what our eyes can see, out to about 2,000 nanometers or 2 microns, which is sort of a factor of 3 times longer wavelengths than what our eyes can see, contain absorption features which we think are going to be important for diagnosing habitability and perhaps signs of life. Now, there are lots of technical challenges to being able to be sensitive to that full range of wavelengths, both with detectors, with coatings of the mirrors, but also actually being able to resolve the planet outside the glare of the star. The longer the wavelength you go, the larger the telescopes or the larger the star shade you need in order to do it.
Good. That's where I was hoping you'd go with that.
So that starts to become quite challenging. So so at the moment, for the exoplanet science, we're sort of focusing on the region somewhere between 300 nanometers and 1,000 nanometers, which is just a little bit beyond what our eyes can see on either side of the short and long wavelengths. But we are actively considering going to shorter wavelengths, particularly because of what you said, that once Hubble is gone, we have no UV capabilities, or no currently planned UV capabilities, to do this incredible cosmic origin science that Rachel was talking about, and solving, this somewhat embarrassing but very important question of where are all these baryons, where's all the missing matter that we think should be there. And by making a telescope that's significantly larger than Hubble, and also making it UV capable, we're adding a capability that we've never had before. And to make that interesting, we have to be at least somewhere around that. For that and the exoplanets, we probably have to be somewhere at least around a 4-meter aperture. Which doesn't sound that big compared to JWST, but remember, we're talking about different capabilities and different wavelengths here, up to something that's JWST size, although not as cold and operates at different temperatures. And then, then that's where the sort of the range we're considering. LUVOIR is considering, as you heard in their Google Hangout, even larger apertures, which would allow you to do even more exciting science, but of course comes with its own technical challenges that we would not face. So together, the two teams are really complementary, and we're really exploring this huge, broad wavelength space. But I want to emphasize that we're also in HabEx, even though we're not necessarily looking at apertures that are larger than JWST, are looking at capabilities that are well beyond what JWST can do in terms of wavelength and being able to suppress the starlight and detect habitable planets.
Mo bigger, mo better. All right. Yeah. So, Andrea, or I'm sorry, Rachel, I just want to put this up because it is a really cool slide, and I was hoping maybe while we're on the subject of the UV and what the kinds of things that we can get from this from HabEx, maybe you could talk a little about this slide.
Absolutely. So another thing that HabEx could do, if it has a camera. So what we were talking about before was spectroscopy, right? Looking for this gas in absorption.
Of course it's going to have a camera.
Well, right. I mean, would we put this up without a camera? That would just be weird. So, yeah. So if we have a camera that is sensitive in even just in the sort of blue optical, wavelength range, then with the exquisite spatial resolution that we would get from space, we can actually take pictures of galaxies and resolve out individual stars inside of those galaxies. So what we want to do is do what astronomers call photometry, right? We want to very precisely measure how bright individual stars in other galaxies are. And now, why do you want to do that? If you can do that, then we can use our knowledge about how stars evolve, specifically what we call a color magnitude diagram. And that's what's shown in the slide there in the sort of top left and bottom left of the diagram, where you see all those dots. Those are the colors and brightnesses of individual stars in the Andromeda galaxy. So this plot is taken from a paper that came from what's called the FAT survey, which was done with Hubble Space Telescope. So Andromeda is, of course, one of the very closest galaxies to our galaxy, and so it was possible to do this kind of study with Hubble because Andromeda is so close to us. But unfortunately, there aren't very many galaxies that are close enough to do this with Hubble. So again, Hubble will sort of run out of galaxies where we can do this, even if we don't just run out of time on Hubble.
Right. I just want to emphasize while you're talking about FAT that the upper right image is the survey itself, and it was basically the stuff in that jagged white square is a rectangle is all of the pointings that Hubble did, and there were hundreds of them to look at that. Look at that galaxy to resolve the individual stars, and that full moon there is just for scale. So that's how much of the sky that it actually imaged, and it took years to make this. So
it was one of the largest Hubble programs ever.
That's right.
Yes.
I just want to emphasize that because it took Hubble a really long time to make this, but it is a super high resolution image, and they only did one corner because that was the most interesting corner. They felt the symmetry of the galaxy. They could answer other things. So. Anyway,
right,
I'm sorry,
and it was already kind of a ridiculous amount of Hubble time, as
exactly,
you pointed out.
Which is very precious.
But it turned out to be really, really cool. I mean, this data, these data are incredibly rich. So let me come back to what you can do with these data now. From these color magnitude diagrams, we can learn about the ages of each of those stars that we see. And we can also learn something potentially about the chemical composition, how many heavy elements there are in those stars. And from that, we can do what we call sort of stellar archaeology. So you can sort of reconstruct when those stars formed over time. And that's what's shown in the little diagram on the right there is the rate that new stars were born over the history of the Andromeda galaxy. And as you can see, stars, were forming more rapidly in the past, and then that rate has declined, and it's declined even more sharply relatively recently. And all of that is super interesting, right? We'd really like to understand why do stars form with a particular rate? Why do they stop forming? What does their rate of formation go down? So imagine that you could do this now for, instead of just one galaxy or a few galaxies, if you could do this for hundreds of galaxies. That's what HabEx would allow us to do. So we could do this for galaxies in different environments, different types of galaxies. Most of those galaxies would be rather small, what we call dwarf galaxies, but it turns out dwarf galaxies are actually very interesting for theorists for various reasons. So we can do this stellar archaeology and actually sort of decompose the galaxies. And of course, as you can see, you can even do this as a function of location within the galaxy, right? So you would be able to see, the stars right in the center of the galaxy formed a long time ago, whereas the ones in the outer parts formed more recently, or whatever the case might be, right? So with this great spatial resolution, we would have spatially resolved star formation histories for these hundreds of galaxies. And this would be super exciting to then relate to the previous kinds of studies that we were talking about. So now we could, for the first time, see kind of both sides of the coin. We could see the stars that are responsible for driving this gas out of the galaxy and for producing these heavy elements and reconstruct their formation history. And then we could also see the gas that's surrounding the galaxy, which of course had to have been put out there by those same stars. So we could really try to put this information together in a very nice and complementary way with this one telescope.
Right. Good. Okay. Well, thank you, Rachel. That is, I think this whole thing is amazing, and as you guys were describing all of this, and one of the things as I do more of these hangouts, one of the things that keeps coming into my mind is, in the same way that in the 50s, 60s, and 70s, and 80s, and even now, where there was this thing called Moore's Law, where computers just kept getting faster and faster. Every 2 years, they were doubling in speed and all this kind of stuff. And I wonder about aperture sizes in space telescopes, because we just keep making them larger and larger. Now, it's not obviously as fast because these things take time to build and they're very expensive, but gosh, we started with the Hubble Space Telescope, relatively small optical primary, and then we got JWST with its mirror segments, and now we're just talking about getting larger and larger and larger, building star shades to put in front of them. So it just seems to me like we're growing in the space telescope arena faster than we ever have before. So this is really exciting stuff. I want to get to some of the comments that are on Twitter right now. I'm seeing some of my familiar faces. And Marty Frederick, hi Marty. This is he's commenting that Future in Space is missing Alberto Conti. He is doing his day job by waving the space science flag proudly for Northrop Grumman today. So yes, we do not have Alberto here, but he's out doing his day job. So thank you, Marty. Andrew Planet is asking, to what extent is it possible to integrate different missions and their distinctive technologies in case of limited funding? I guess that means, what if you guys don't get picked in the decadal survey as a mission? Is there something we can do with existing missions to combine and do some of this work?
So I would ask, I would say we should ask Bertrand about the Rendezvous mission, which he probably knows something about.
The Rendezvous mission, what's that?
Right, so there's this project at the moment. So you know about this telescope called WFIRST, which is supposed to be launched in...
WFIRST, right, Wide Field Infrared Survey Telescope.
That's right. She's supposed to be launched in the mid-2020s, and it's essentially a wide field imager with applications in dark matter studies, but it will also have a coronagraph for studies of exoplanets. Not exactly the types of exoplanets we're talking about here, mostly giant exoplanets, which are a bit brighter, and a smaller amount of them than HabEx could do, and not in the habitable zone. But it would already be an extremely interesting mission. And then lately, it's even been considered that there could be a rendezvous with WFIRST where a star shade might be launched after the WFIRST and rendezvous with it to also try this star shade high contrast imaging technology on the WFIRST. So,
wow, that would be cool. That would happen sooner too.
That's right, and it would be very interesting also technologically to demonstrate some of the methods that we've been talking about. Because obviously for a star shade, it's very difficult, or for any of this technology, it's very hard to demonstrate everything end to end before you actually fly these technologies. Okay. So that would be a great opportunity, and
that would be amazing. I hope they do that. They should do that anyway, as a matter of course. They're building WFIRST, right? They're going to launch it. I mean, how much more could it? Just build a star shade and throw it in front of it.
They are now considering what changes they have to make to WFIRST to make this possible. It turns out that the changes are relatively minor.
Good.
Good. Even if you don't launch the Starshade, you want to make sure that you have that it would still work if you did have that opportunity.
Okay. Yeah, you want to launch the very first telescope that's probably Starshade compatible, so that if the choice is made to launch this Starshade, then you're ready for it.
All right, who do we call up? Is it Mark Postman? Mark Postman? Are you the guy? Yeah, you need. So think about this.
No, you need to talk to the Decadal Survey. That's who you need to talk to.
Mark Postman was the guy. He was one of our first hangouts, and he told us about W first. So I just wanted to give a shout out to him. So Patrick Freeman or Fryman, I'm sorry if I'm mispronouncing it, is asking, he's asking, technology evolves rather fast. Couldn't we have a better image resolution quicker? And, well, Patrick, I mean, first of all, I think what you're talking about is this idea that when we build space telescopes, we have to plan way far ahead, so we're using existing technology, but by the time it gets launched, it's already obsolete. If that is the spirit of your question, then it sounds to me like, Scott, and maybe Bertrand, you can comment on this too, that you guys are kind of looking ahead, aren't you? I mean, when they designed JWST, for example, they had to kind of work into the project stuff that hadn't been invented yet, and they invented it while they built the telescope. Now, in part, it was one of the things that delayed it. But are you working? Is that part of your thinking in a project like HabEx, where you have to kind of think about things that don't exist yet, or do you just build existing resolution technologies into your design?
So I think there's two answers to that question, but one answer is certainly that we can, when we're thinking about missions in the future, we definitely are considering technologies that are not yet mature, right? So NASA has NASA speak that defines how mature a technology is.
Right, space ready or something, right?
Technology maturity level, TRL level, and it has to be a certain TRL level at certain stages in the development of the project. Otherwise, the project has to be de-scoped or something like that. So we certainly think about very nascent technologies, and part of the reason why these missions can cost a fair amount of money is because we have to develop these technologies. So, for example, at JPL, they are developing chronograph technologies for WFIRST, which Bertrand mentioned. The other part of the answer to that is that why do we have to make sure these technologies are mature, and why does it cost money, and so why are the technologies that we sometimes launch or often launch are out of date by the time we launch them, so to speak? Well, that's because we want to make sure they work. We're not going to be spending $1 billion or several $1 billion on a mission that we don't know 100% the technologies are going to work. So I don't think the taxpayers would be happy about that, and I'm pretty sure we wouldn't be happy about it either. So sometimes you have to sacrifice the state of the art for something which you know is reliable and actually works, and I think that's the other answer to the question.
Yeah, I may add just something about this problem of imaging Earth-sized exoplanets around other stars. I mean, it really requires not only spatial resolution, but it's really the conjunction of spatial resolution and contrast, which has never been demonstrated at that level so far. So there are ground-based telescopes which will have better spatial resolution at JW or HabEx, but there are no telescope existing on the ground or planned in space that will have that combination of contrast at very high angular resolution. So this is really innovative in that sense. We're getting close to that in the lab, but it's never been done in space.
Yeah, I think people fail to appreciate the luxury that scientists and astronomers had with the Hubble Space Telescope and its ability to be serviced over the 25 years it's been up in space, because, or 26 years now, because they could build it with perhaps more tested technology that maybe wasn't, that was much more mature, as Scott points out, but as new things became available, new infrared detectors became available, they were able to be upgraded into the spacecraft, and that was a real luxury. And so that brings me to something. I have a question for you guys. So Hubble was in Earth orbit, JWST is going to L2, WFIRST is also going to L2, I believe. Where is this thing going to live?
L2.
L2. Okay.
Yep. It's all L2. It's all L2 from here on out.
Okay. It's L2 all the way down.
Well, at least for the flagship missions. I mean, it's just a much better environment. for a lot of the things we're trying to do. I mean, one of the things you don't want, right, for what we're trying to do for high contrast imaging is your telescope to get hot and cold and hot and cold and hot and cold, because as you can imagine, that's going to change the structure of the telescope, and you'll get different diffraction for your coronagraph or whatever, and that's bad. Your mirror will change slightly in shape. And so we want to go to an environment that's very thermally stable, and when you're orbiting the Earth, going in and out of the Earth's shadow, that's not a very stable environment. Yeah. So that's part of the reason why you can't do this with HST, for example.
You know what, Harley? This reminds. You know what we should do? Like, we've had these hangouts where we talk about cislunar space and building habitats to Mars and getting things in between here to help us understand or live long-term in Mars. You know what we should do? And this is the first time you're hearing it here first, folks. You should build a space station in L2, and we should put people there as kind of like attendants.
Well, you should know that people are thinking about making the telescopes at L2 serviceable now.
Well, it's as Scott was pointing out. Actually, it's required to make
congressionally mandated now.
Yeah, it's mandated, legally mandated by Congress that they will be serviceable.
Why what? How can you mandate? What are we going to service it with?
Well, we can get that's actually a terrific. That's a whole nother topic. Just
I did not know this. Okay, so all these telescopes. Not JWST.
They all have to be serviceable.
HabEx, LUVOIR, the far infrared surveyor, X-ray surveyor, all have to be serviceable.
W first.
W first.
And also from W first on. I'll be darned.
So NASA, I think it's about 6 months ago, NASA finalized contracts with 4 aerospace companies to design first, build and deploy eventually an operational site habitation system somewhere in the lunar vicinity, presumably a libration point, but there are a variety of other orbits there. And at least one of those companies, I think maybe 2, one of those design teams is looking at servicing scientific assets at the libration points.
Oh, wow.
So there's other ways you can do it. Now they're going to look at Earth-Moon libration point, whereas LUVOIR or HabEx or one of the other missions will probably go to a Sun-Earth libration point some distance further away. But you can move these. You can move fairly trivially these observatories from libration point to libration point. So you may bring it to a habitation site for servicing.
Wow,
you can use robots.
That's amazing. I did not know that. Harley, suggestion, please write this down. Let's have a hangout where we talk about that, because that's huge. I didn't know that these missions were being mandated to do that.
We can just take over this discussion from our.
No, I don't want to do it now. That is something
there's a whole body of work being done, various teams that are looking at human and robotic operations beyond the immediate vicinity.
Cool.
Great topic.
All right, that is okay. Good. So stay tuned, folks, for future ones. That's great. George Caldwell, welcome back. It's good to see you again. He is in Spain, he says, so he's got a bad internet. Now, I hope you're not saying that it's bad throughout Spain. It's just you have bad internet right now. But he would like to know views on the Drake equation, as well as some info on planet types we've found. So one of the things that I know that Kepler has done is it has helped us. One of the Drake equation is this long series of terms that has to do with the probability of finding another civilization. And one of the terms in there I know that Kepler has helped with narrow down is the number of planets that have habitable, or the number of stars that have habitable planets around them. Kepler has helped a lot with that. So do you guys have any comments or anything you want to add to that? With anything about the what are your views on the Drake equation? Is it wildly inaccurate these days? Are we narrowing it down? Any views?
I mean, the Drake equation is just a way of parameterizing our ignorance in terms of the number of intelligent civilizations in the galaxy. I'm not saying it's not useful. It is. And maybe 100 years ago we knew the answer to none of the terms in the Drake equation, and now we know the answer to the first 3, I think, to at least an order of magnitude. And so that's pretty good.
Better than a wild guess, right?
It's better than a wild guess. The problem with the Drake equation, of course, is if any single one of those n terms is 0, then the answer is 0, and we're done. So its usefulness is limited by that. In terms of eta Earth, which is the number you're talking about, the fraction of stars hosting a planet in the habitable zone. That's a number that Kepler is trying to measure, and is measured to, depending on who you ask, a factor of 2 to a factor of 10. It turns out to be a very difficult number to measure, but it's a number that figures actually fairly crucially into the design of our missions, because we need to know how many habitable Earths are out there, so we need to know how far to go out and how big of a telescope we need. So that's something we're worried about and thinking very hard about when designing these missions, both HabEx and LUVOIR. In terms of the variety of planets, I think if we've learned anything in the last 20 years of searching for exoplanets, it's that Mother Nature is way more imaginative than we are. We kind of imagined that also, very, very, naively, we imagined all solar systems would look like ours, and it turns out that, pretty much every kind of planet you could imagine, Mother Nature has found a way to make.
Great. Okay. Well, Andrew Planet is asking a really good question. Maybe this one's for you, Bertrand. I don't know, but I'll read it out and you guys can decide. He's asking, how will they align the star shade with the telescope? Some sort of parallax sensors or something else? How do you line them up?
Right. So there's at the back of the star shade, on the side that faces the telescope, there's an array of LEDs. So basically, like an artificial star, which is there at all times. So that's being detected by the telescope, and so we would be using radio ranging to actually feedback that information and move the star shade. Turns out you're actually moving the star shade to align it in this line of sight from the telescope to the star. You're not you're moving the star shade rather than the telescope. But that's the way you do it. So the star shade is really emitting its own light that's being detected by the telescope.
So are we talking about this thing here?
I think so. Yeah, that would be where you would put your array of LEDs, and then basically this light would come at a different color or wavelength than the light of the star or the planets you want to detect. So you would use a dichroic, basically a piece of optics that separates wavelengths. On one side you would detect starlight, real starlight, and planet light, and on the other side you would detect your star shade, and then you put the two spots on top of each other, basically. Okay. By moving the star shade.
All right, good question, Andrew. Thank you. All right, and he has one more here. Let me see. This is from Andrew Planet again. Don't we want to go further into space? L2 is the ideal motivator, as we'll have good reason with the servicing of craft. And I think that's what you were talking about, Scott, earlier. Maybe going to, or no, maybe it was Harley looking at these other L points that may be further out.
Yeah, I mean, I think it's a step. I mean, a mission to Mars is very much on the table and being discussed by NASA, a manned mission to Mars even, and so we're being serviceable at L2 with actual humans is one step in going in that goal. So I think there's a overall plan to get us to Mars. I don't know what the time scale for that
2030s.
but going to serviceability to L2 is certainly one part of that story.
Okay. Well, great. All right. Well, we are out of time, folks. I'm going to have to stop the hangout there. I'm sorry, Rachel. Unfortunately, I'm going to have to mute you, I think, because of the echo. Okay. So, but I want to thank you all for joining us. This was a great hangout. HabEx. So something to keep your eye out for in the next decadal survey. I wish there was a way the public could vote, kind of like an American Idol, where you can kind of like text in and say, yes, do you support the HabEx mission? Text yes to whatever it is, and then the public can weigh in on these things.
So I mean, the public can weigh in, right? They can vote. And they're free to talk to their representatives in Congress.
Yes.
So they can weigh in. In fact, they are probably one of the most important supporters of these missions.
Now, are you in competition with LUVOIR, or is this a?
So the way we like to look at it is that we don't know what the space of possible constraints are in terms of financial, political, technological. So we're trying to span the full range of constraints, and wherever we end up, then we're ready for that scenario.
Okay, well, we'll keep an eye on things. I really hope that you guys get some funding for this. I hope it gets it into the decadal survey and gets a green light, because life in the universe. What's more important than that? So, I mean, that's huge. So I hope it gets a lot of support. Harley, we are moving, I think, next month to Thursday. Am I right?
We'll talk about that. That is the plan.
Okay, so keep an eye out. We're moving from Fridays to Thursdays, starting in in September. Please follow Deep Astronomy on my Twitter account. I will let you know when that happens. If you haven't subscribed to my YouTube channel, the Deep Astronomy YouTube channel, you must do so. Also follow it on Facebook, also at Deep Astronomy, and you'll be able to get notified of events as well. So I want to thank all of our guests for joining us, Dr. Scott Gowdy, Dr. Rachel Somerville, and Dr. Bertrand Meninson from JPL. All of you guys, thank you for taking time out to join us. We hope when things get worked out, you'll come back and give us an update. Will you do that?
Sure.
Pleasure.
Indeed, very much. Great work, guys.
Yes, thank you all very much. Thank you guys. Thank you all for watching. Also, thank you for commenting on Twitter. Also, next month, I'm hoping to have the chat ability returned to us. So I will keep you posted on that. Okay. Well, on behalf of Harley Thronson, I want to thank you all for watching. And this was this month's Future in Space Hangout. And as always, keep looking up.
Thanks, Tony.